So when you're looking at something like your coordinate system, and let's hold on, we can adjust the lights. When you look at your coordinate system, you're familiar with all the directions, the ups, the downs, left and right. And what we're going to do is we're going to label these A vector, B vector, C vector, and D vector. So when I say A, you're going to think up. Now, this is advice or a warning, more of an advice. It doesn't have to be A is associated with this direction, D is always associated with that direction. I could call that Petunia, that Oxford, that Mississippi, etc. As long as I define what it is. All right, good. Now, for these other vectors, the in and the out, you'll see these two symbols. Now, they don't have to be in these positions. Really, they're right there. But I've labeled these vectors E and F. So E, which is governed by this symbol, is vector coming out of page. And then that is vector going into page. So the circle with the dot represents the arrow coming at you, the arrow or vector coming out of the page. The circle with the crosshairs is the arrow going into the page. It's the vector going into the page. Now, one of the things that you guys need to be very aware of is I am a fanatic about using Physics 213 as a way to develop your three-dimensional visualization skills. I need you to develop that because really, it's not needed only for physics, it's needed for all the different subjects that you deal with. Being able to see chemicals and how they're bonding together, materials, how they're in particular layers. For the geology, you need to understand how certain pockets of different materials rise up and down through rock. Visualizing things in 3 dimensions is critical, and this will help you with some basics. The thing about 3D visualization is that I could sit here and I could rotate the paper like this. It doesn't change the labeling. Instead of A going this way, A is now going that way. The labels don't matter, the directions don't matter, and now E is heading up towards the ceiling. If I hold the paper like this, now E is coming at me. Don't restrict yourselves with holding one vector to one specific direction. I would say that words like left, right should not be used. Try to get away from those and instead just go that way and this way. Because a lot of people, when they go, oh, B is left, and then I rotate it like this, and then they go, well, B is still left, and then they blow their minds. Just say now, B is that way, and B is this way. I mean, you could just rotate things around. It doesn't matter. Now, the right-hand rule comes from a math, trying to think of the right word, a math phrase or something called, now what we're going to do is I'm going to present you with two choices. A determinant, you don't have to know this word, I'm just telling you where it comes from, of a 3x3 matrix. Now for the, if I taught 211, those students would learn this. And it looks something like this. And you have to get the determinant of this, and it involves another type of mathematical problem. You don't have to use this. Now, one of the things, and this is how it was introduced to me, you could sit there and they talked for about 15-20 minutes about how to take a determinant, and everybody's minds were just fried, or you use your right hand. So with the right hand rule, you could either do this, or now really this A, B, and C is not related to this. It should be more along the lines of first vector, second vector, and third vector. So the A vector is the first vector that you use. The B vector is the second vector that you use, and obviously C is the third, the resultant. Now, with the first vector, now before we continue on with this, the right-hand rule, now first off, I must say that as a left-hander, I'm offended by, once again, being oppressed by our right-handed masters. But right-hand rule, you have to be consistent. So what I typically do is I put my left hand in my pocket, or I just forget about it. And the right-hand rule is simply like this. First vector, second vector, third vector. First vector, second vector, third vector. Watch how I'm doing this. First vector, I'm pointing in a specific direction. It doesn't really matter right now, we're learning the motion. Also notice that my hand, fingers, and forearm are all locked in one line. So if the first vector was that way, I point in this direction. If the first vector was that way, I point in that direction. Always with the right hand. Second vector, you notice that only my fingers bend in a particular way. They can't bend backwards. There was one student who was double jointed and she could just flop her whole hand over and touch her forearm with her own fingers. And I was like, you need to talk to a specialist because I think you were abused as a child. So, but you notice most normal people can't bend their fingers backwards. So in a normal circumstance, if that was the first vector and that was the second vector, 1, 2. Now if I said that was the first vector and that was the second vector, 1, I can't bend my right hand backwards, but what I can do is I can rotate my whole arm. This is a valid direction for the first vector as well. And then second vector like this. Now the third vector, all you have to do is ask yourself, where's the thumb? First vector, second vector, third vector, up, or that direction. First vector, second vector, third vector. The third vector is always in the direction of the thumb. we could either determine a 3 by 3 matrix or just use your right hand. Now, there are some people, tutors, professors, TAs, all that stuff, they just go, oh, right hand rule, it's this is all you just look at it, just do this. The way that I was brought up is they believe that a more visually dramatic motion is a lot better than just this. If that's the way that you do it, fine. But the way that I do it, I've had an excellent track record with people just picking that up. I taught a bunch of physical science students this, and they learned it. I keep trying to teach my niece how to do the right hand rule. When she was 3, she just said no and just walked away and played with her dolls. I'm hoping this year she's 8. I think I've got a good shot at it. I'm really trying to figure out when this thing can happen. So, right hand rule, first vector, second vector, third vector. So let me write that down. Fingers, palm, forearm, point in A's direction. Fingers curl in B's direction. And they got to, if necessary, you can rotate the arm. Third vector, thumb points. The third vector points, or the thumb points in this direction. Excellent. Oh, that's awesome. All right. So first vector, second vector, third vector. We have considered, what if we have, I won't teach it to you, but what if we have a person who has no right arm? We've already figured it out. But since everybody has their right arm, we're not going to go teach you that. So let's play the game with this. I'm going to come up with some. Now, there are some restrictions. So restrictions are an invalid way. Now, mathematically, you can work with these, but in a 213 format, I'm not. I can't give you... Oh. Well, I need my game. It's going to come back, but all right, fine. Huh? Does that make you happy? Okay. You're welcome. So I can't do double vectors. So A cross A is not allowed. I'm not going to do 180 degree vectors. So in this particular case, for this picture, so A cross C is not allowed. So for 180 degrees, I'm not going to do it, and I'm not going to do it for the same vector. Now here is our game, and what I want to do is give you 5 vectors. A cross B, B cross A, F cross D, C cross E, and whatever, B cross C. Okay, so those are going to be the 3 vectors that we're going to do. Now, initially, the first step in learning this game is that we're going to work from the vantage point of the screen. So everything is in relation to this screen right now. Next Tuesday, the Tuesday before the test, what I'm going to do is I'm going to draw a right-hand rule game up on the board, and you're going to write down all the problems, and then I'm going to take that off the screen. Because what I need, well, a lot of times there are people who, they look at the screen, they look at their test, they look back at the screen, and the screen's perspective is different from the one on the page, and people get confused. So what I want to do is I want to simulate a testing situation for this right-hand rule game, and we'll do it on Tuesday, and we'll do it together. Bottom line is, you're looking at the appetizer problem for test 2. This is it. So you're going to be given 5 one-point right-hand rule games for a total of 5 points, and so that'll be the appetizer. Now, first problem, A cross B. So, and I will stand from the perspective of the student. A is towards the ceiling, so that's the first vector. B vector is towards that wall, which means that the thumb points out of the page, which means what vector? It'll be E, correct. Now, B cross A, some of you may say, well, if A cross B is E, then B cross A is also E. That's not the case. But if you take 1 times 3 and 3 times 1, you get the same answer, not in vectors. If we go B cross A, B is that direction, A is towards the ceiling, thumb now points into the page, and we're dealing with an opposite vector. F cross D, F into the board. Now D is that way. I can't bend my fingers over, so what I do is I rotate my hand, and then the thumb or the fingers head that way. Thumb points towards the floor. Towards the floor is C. C cross E. C is down towards the floor. E is out of the page. Thumb points that way. We're looking at B. And then for the last one, B cross C. B is this way. C is that way. Thumb is out. B cross C is E. And so that's how you do it. On the homework, you have a right-hand rule game, so you can play it and take a look at it. I'm saying this on the video. I'm primarily saying it, well, I'm saying it to you, I'm saying it to the people watching, but most of all, I'm saying it to the person who isn't sitting in seat 20 or 52. This class has about 160 students. 99 have signed up. So there are a lot of people not in the room learning what the right-hand rule game is. Occasionally, I get this as a question. Dr. Eschenberg, I'm like, yeah, what do I do with this? And I'm like, what do you mean, what do you do with this? I'm serious, I don't know what this is. And this has happened on 3 different occasions in the test itself. And what does that communicate to me? They never went to class, they never looked at the videos, they never did the homework, and this thing just nails them to the wall. And it was funny because one person was asking me that, and the student sitting in like the front row aisle chair just kind of looked up, rolled her eyes, because she was just like, I can't believe he just said that in front of the class, because he just basically admitted that he had no idea. So this is going to be on the test. It's a simple, quick, should be quick 5 points. Well, let's do this. This is how I typically do A, B, E, B, A, FDC CEB DCBCE. Okay, there we go. Now, one of the things that you notice is the relationship between those two. If you reverse the order of the vectors, you flip the direction. So A cross B is negative of B cross A. So A cross B is not equal to B cross A. A cross B is equal to negative of B cross A. And so that is the right-hand rule game. Yes?
So when we look at our notes, like after class, we should get the same vectors?
You should get the same answer. Because if I held it like this, so I'm going to hold it like this, just on the screen. A cross B is E. A, B, out of the page, E. But if I held it like this, A that way, B this way, it's still out of the page. It doesn't matter about the orientation. You can have it like this, you can have it like that, you can flip it over like that, you can hold it upside down. Those vectors will still be the same direction, or the answers will be the same. There was one student who, in class, asked me, I've only been able to do the right-hand rule game like this, by just holding it up in front of him, because it's similar to the way that we introduced it. And he said, can I stand up and hold the paper and do the test like that? And I was like, yes, but I must take photos of this. And I took photos and it was amazing. So it's really, I understand how corny this looks. But when you get 160 people in the same room doing it at the same time, it's kind of cool. I at least like it. So. All right, let's do this. I'm gonna throw a rock at that thing outside. Oh, garbage people. All right. So the right-hand rule is very useful for a lot of different things. The first of which is the right-hand rule game. But the next thing is a torque bar. If I had to guess what's on the test, I would say right-hand rule game, Atwood's machine, with energy and friction. Then I would go rotation, most likely with an alpha not equaling to 0. It'll either be rotation with alpha not equaling 0 or rotation with alpha equaling 0. It'll be one of the two. And then the last thing, torque bar. So that'll be the third test, or the second test, excuse me.
Dr.
Yes?
Didn't you say in the tutorial that the Atwood's machine problem would be pretty similar to problem 8 on the homework?
Yes.
Is that correct?
Yes, okay. But from the perspective of you're only using energy.
Right.
Yeah, just like we did it in tutorial.
Okay.
Now, one of the things that I will say about the second test is it's not going to be as just blatantly straightforward as test one. We'll start exploring some more problem-solving techniques and build on what we've covered in test one. Because boring tests aren't fun. Well, I call them celebrations, but that's another discussion. So for the torque bar, we'll start simple. These bars will not have mass. So M1 is 5 kilograms, and I don't know what M2 is, and I'm looking for M2. And this is R1, and that is R2. R1 has a distance of 1 meter. R2 has a distance of 0.5 meters. And what is it doing? It's at rest. It's doing nothing. So by the fact that it's doing nothing, you can get so much information out of simply that. How can it possibly be? What can you get if it's doing nothing? Well, if it's doing nothing, it's not moving up or down. If it's doing nothing, it's not moving from left to right. If it's not moving, it's not rotating. So it's not rotating, and it's not moving linearly. Now, you've heard me mention that there is a phrase, or you've heard me say a phrase, translational equilibrium. For translational equilibrium, the sum of the forces is equal to 0. So for MA, this particular A is equal to 0. By it not rotating, it's in rotational equilibrium. So for rotational equilibrium, sum of the torques is equal to 0. And if the sum of the torques is equal to 0, that alpha is equal to 0. So by it not doing anything, you can say with certainty that it's not moving up or down, and it's not rotating clockwise or counterclockwise. Now, to label all our vertical forces, which I'll do in red, the two masses are pulling downward. If there were no other forces, this torque bar would just fall downward or down the page. But there's another force acting on it. Now, what I've just drawn is the ground beneath the fulcrum. And the ground beneath the fulcrum is holding up the bar. More importantly, the bar is feeling a force upward. So you have two forces pulling down. The bar is not accelerating downward. So there must be a force pushing up. And so that is the force of the fulcrum on the bar. Now the question that I'm going to have is, what is M2 and what is the force on the fulcrum? Now, the way that the unknowns are set up, you attack torque first. You say, well, this thing is not rotating, so the sum of the torques is equal to 0. Then what did we know, or what did we learn about torque? That torque, just dealing with magnitudes, is the force multiplied by the distance from the force to rotation point. So if you take the force and you multiply it by the distance from the force to the rotation point, you've got the torque. We're going to choose that point right there at the fulcrum as our rotation point. And I'll get back to this later, but you could choose any point on this bar as your rotation point, and the problems should just work out just fine. The sum of the torques is equal to 0. And what I'm going to say is there are two forces about that rotation point. Therefore, we have two torques, M1GR1 and M2GR2. Now you notice I haven't put any signs down on the page. And you've also noticed that there's no, where's F? If you've got a force, you've got to have a torque. Well, in a way, I took advantage of the situation. Remember when I was over here at the door, first describing torque. The door hinges are on the right-hand side, so it would be kind of dumb to push on the right-hand side. So you push on the left. That applies a torque to the door, and the door opens. But as I move my hand towards the fulcrum, towards the rotation point, it gets harder and harder. Why? Because the distance is decreasing, therefore I have to increase the force. But what if I push the force at the rotation point? That door isn't going to open. Because you can have an infinite amount of force, but if that distance is 0, infinity times 0 will always give you 0. So what we did is by choosing that as the rotation point, the distance from the force to that rotation point is 0. So in the equation that we're using here, it is unnecessary to use this force because the distance is 0 and it would go away. So all you're having to do is if you choose that as the rotation point, look at the other forces that would cause rotation. It is one of the wise selection of rotation points can eliminate unknowns temporarily. And so what we're going to do is now the only unknown is M2. Let's look at the signs. That force there is down. What you do is you always start, if that is the rotation point, the distance is from the rotation point to the force, or left. the force itself is down. So using the right-hand rule, because torque as a vector is d cross F, and now the directions are critical. It's not F cross D, it's D cross F. First vector, second vector, third vector, thumb out of the page, or positive. Now looking at the other force, that's the distance vector, that's the force vector. Distance to the right, force down, thumb is into the page. So this is that type of vector. When you have when you have a symbol like this, that represents positive. When you have a symbol like this, it represents negative. So our signs are positive and negative. Now, one of the interesting things before we solve this is just more of a discussion of 3D visualization. So this is from the side, and this is going to be the view from the top. From the top, the first vector is like that, the distance vector, because this is the rotation point. The second vector, its distance vector is like this. Now, if you're looking at it from the top, in both situations, that force vector is into the page. So if I was to do this again, the torque vector, D cross F, thumb points this way. And then D cross F causes the torque to go this way. These are the torques that are opposing each other. So in order to visualize, I mean, we all could sit here and think that about, you've got two forces pushing against each other. You just add up the forces and the resultant is where it ends up. With torques, they all have their own opposition to each other. And then the winning torque would cause this to rotate in whatever direction that the torque demands. But in this case, the two torques are equal to each other. So the net torque is equal to 0. And so this shows you how they oppose each other. And from our perspective, we're looking down into the page. From this perspective, we're looking from this direction. So we're looking in that direction. And so this is away, and then that is towards. So just to give you more motivation to visualize this stuff. Now now to solve this, 0 equals this minus this, so M2GR2 is equal to M1GR1. G's cancel. What am I looking for? I'm looking for M2. So M2 is equal to M1R1 over R2. M1 is 5, R1 is 1, R2 0.5. So M2 is equal to 10 kilograms. And so that is a simple torque bar problem. All right. So when doing these torque bars, once again, yes, question?
You said from the top, and you said we were looking at it from the bottom.
Well, what I'm doing is I'm not changing the perspective of the person. This is the person who is watching this here. So really what this is kind of looking like this. So the person, so you understand now. Okay, good.
So how do you know the signs for the M1GR1 and M2GR2?
The signs are totally determined by the right-hand rule. If the right-hand rule says that the vector is coming out of the page, it's positive. If the right-hand rule says the vector goes into the page, it's negative.
So one of them was negative and one was positive.
Correct. In M1GR1, it produced a vector coming out of the page. In M2GR2, it produced a vector going into the page. So into the page, negative. Out of the page, positive. Positive, negative. And so that's how it determines. So you can either sit there and do the determinant or just use your right hand and it determines the sign. Out of the page, positive. Into the page, negative.
Like, which direction is out of the page?
Which direction is out of the page?
Yeah.
Well, in this particular case, out of the page is right at you. In this case, out of the page is this way. Out of the page is out of the page. Do you understand?
No.
So if I have the page like this, out of the page is at you. If I flipped it like this, according to this symbol, out of the page is this way. It's out of the page.
Put the page flat on your desk because like that's how.
Out of the page then means this. Into the page means that. We'll talk.
Okay.
All right, next. Continuing on to this problem, because we haven't solved for one other thing. The other thing that we know about the bar is it's not moving up or down. If the bar is not moving up or down, the sum of the forces is the vertical is equal to 0. In this example, yes, that's what we're doing right now. What we're determining here is what's the magnitude of this force. That force has to exist because those two forces are pulling down. Now, one of the things that that we do is, if it is up, it's positive. If it's down, it's negative. So F minus M1G minus M2G. So anything pulling down, negative. Anything pushing up, positive. The fulcrum is pushing up on the bar. So M1G plus M2G is equal to F. And M1 plus M2G is equal to F. So 5 plus 10 times 10 is equal to 150 newtons. Because M2 was 10 kilograms, so we got 150. So that is the force of the fulcrum on the bar. Yes?
On the first part, where it's sigma Fy equals 0.
Yes.
Are the M1G and M2G supposed to be in parentheses?
Are the M1Gs and the M2Gs supposed to be in parentheses?
M1G minus M2G, close parentheses?
I wouldn't say it's necessary. I mean, you could write it like this. That's algebraically equivalent. Your choice. I don't see any great need to do it that way. So, yes.
Why is G just 10 and not -10?
Okay, just as a review. The reason why we use G as 10 is in reality A is negative 10. A is the acceleration of gravity caused on an object. And since down is negative, we use negative 10 for A. G is used as a magnitude. G is positive 10 and always positive 10. And why is that? Because what I rely on is logic in saying, well, the force is down, so it's got to be negative, so it's negative mass times 10. But if I'm pushing down on the table, I know that the normal force is up, but it's still related to mass times gravity. If I put a negative sign in there, I'll have to remember to add another negative sign in there to make it go up. And then I'm taking negatives of negatives. And one thing that I've learned is taking of negatives of negatives of negatives of negatives just gets me confused. So, but there is one thing that I do know. Normal force is up, normal force is positive. The weight pulling down, that's negative. I don't want to worry about an extra negative sign wandering around there, because then I have to cancel it out somehow, and then I get confused. So that's really why. Now, we've done the problem one way, let's do the problem another way. We still have M1G, and that M1 is equal to 5 kilograms. We have the fulcrum over here with a force, and then I have an unknown M2 pulling down with a force of M2G. This is R1, which is 1, and then R2 is 0.5. One of the things that we can gain from observing the bar not doing anything, yes, it's not moving up or down. But we've also noticed that it's not rotating around this point. Now, this is the lesson. So we know for a fact that it's not rotating around the fulcrum because it's not acting like a teeter-totter. But we also know that it's not rotating around the end point here. You don't have to choose the rotation point at the fulcrum. You don't have to do it. If it's not rotating in any way, you could pick any point. I could pick that as the rotation point. I could pick this as the rotation point. I could pick that as the rotation point. Any of those points will work. Now let's show that. I'm going to choose that as my rotation point. I know that it's not rotating around that point, which means I know that the sum of the torques around that point is equal to 0, which is M1G R1 plus R2 and F R2. The distance that force is away from this rotation point is R2. And the distance that this force is away from that point is R1 plus R2. Now let's use the right-hand rule. In both cases, the distance is to the left. In M1's case, the force is down in this direction, which means the thumb is up, so positive. The distance from there to there is to the left, but in the case of the force, it's that direction, thumb into the page, or negative. The only unknown in this equation is the force. I know what M1 is, I know what R1 and R2 are, I know I'm on Earth, gravity, but the reason why I chose the end point as the rotation point is because this mass, this unknown mass, has no effect on rotation about that point because the distance from that point to the force is 0. And because it's 0, you don't have to worry about it. So F R2 is equal to M1G R1 plus R2 F M1G R1 plus R2 R2. M1 is 5, G is 10, R1 is 1, R2 0.5, R2 0.5. So 50 times 1.5 divided by 0.5. And the force we get as 150 newtons. So it checks. So from two different rotation points, we're able to get the same answer. Regardless of rotation point, it is the same physics problem. So whatever rotation point you choose will have no effect on the results. You'll get the same answer. And we could do this the same way to get M2. Sum of the forces is equal to 0. That means F minus M1G plus M2G. I'm looking for M2, so M1G minus F is equal to M2G. M1G minus F over G is equal to M2. M15, G10, force 150. Did I blow this? I think I got a negative answer. Wait. Oh, what did I do wrong? I heard a your. I didn't hear anything after that. So that's up. This is down. That should be down as well. So negative, negative, negative. Because I knew things were blowing up when I had a negative number. M2 is equal to 10 kilograms. So you should be, obviously, we should all have positive mass. If we get negative mass, we should call Stockholm, and let them know that we're coming to get the Nobel Prize. And so you could do it two different ways. It doesn't matter. The rotation point does not have to be at the fulcrum. Now, one last example. You could do all sorts of interesting things with you could have forces down. You could also have tensions up. So I'll have a string tied to the end of that bar. And this particular mass 2, if M1 is 2 kilograms, M2 I'm going to make as 50 kilograms. So the question is, what is the force on the fulcrum, or from the fulcrum to the bar, and what is the tension in the string holding up the far end of the bar? And the interesting thing about this particular problem was I was giving a test review session to a bunch of 213s, and in the middle of the review session, I guess they had an organic chemistry test, like 2/3 of the class just got up and left, which is fine. I don't get upset. But then when they all left, the students asked, could you give us a torque bar problem that could possibly be on the test? And I was like, possibly? I'm saying this to myself. I'm gonna do a test problem right now. And I wrote that problem up on the board. I did it in front of them, and then I put it right on the test. And then there was a big discussion amongst the students who said, like, you should have stayed. He did the test in front of us. So I don't punish those who leave, but I do reward those who stay. There's a difference. So in this particular problem, you know that it's not rotating, it's not moving up or down. You could choose, probably the best thing that I would do is I would choose the rotation point to be the fulcrum. What does that do? That eliminates force from being considered for torque. So if that's the case, then the sum of the torques about that point is equal to 0. Now, there are 3 forces that are separate from that rotation point. There is M1G R1, the distance from there to there is R1. We have M2G R2, the distance from there to there is R2. And then we have the tension there to there, R2 plus R3. And then the tension up, which is this. So we have our 3 parts to the problem. Now we use the right-hand rule to determine the signs. Left, down, out of page, positive. We have right, down, into page, or negative. We have right, up, out of page, or positive. Now, a lot of people tend to say, well, you just, the way that they do it is you add up the twists. If it's clockwise, it's positive. If it's counterclockwise, it's negative. Some even say forces on the left are clockwise, forces on the right are counterclockwise. I prefer to use the right-hand rule. We're looking for tension. M2GR2 minus M1GR1 equals R2 plus R3 tension. G M2R2 minus M1R1 divided by R2 plus R3 is equal to tension. So 10, 50, 1, 2, 1.5, 1 plus 2. So 50 minus 3, 47 times 10, 470. 470 divided by 3, 156.67 newtons. And that gives you the tension in the string. Now the last part, to get the force,
How do you know that the torque is 0?
because it's not rotating. One of the things, when you see something like this, and I go, oh, it's rotating, that would just be rude. So for something like this, if I say torque bar problem, this thing isn't moving. It's not moving, so then you can say the sum of the torques is equal to 0. Probably you could ask during the test, is that moving or is it not moving? And I would stare at you funny and then just say, it's not moving, and walk away. Now, you could do this one of two different ways. You could either A, choose the rotation point to be at tension to find F, and do the sum of the torques again. I have found that now that you know what the tension is, you can find force really quick by just summing up the verticals. So 520 minus that answer, 363.3 newtons. And so that would be the answer. So one of the things that it's just a procedure that you do again and again is choose rotation point where one unknown is irrelevant.
Dr. Eschenberg,
Mm-hmm.
when you did F plus T minus M1G minus M2G,
Yes.
did you redo the right-hand rule? to
No.
the signs of those?
With the sum of the forces in the vertical, I'm summing vertical forces. I'm not summing torques. So when it comes to summing vertical forces, up is positive, down is negative, and the right-hand rule is avoided. You could have chosen this as your points, sum of the torques is equal to 0, and then go about and do the same thing with that you did in part 1, but you would get the same answer that you would for this. The advantage of this, in my opinion, is summing vertical forces is a lot easier than summing torques. Either way, I mean, I could do it the other way, and I would get the same answer. But I'm pointing out to you how to do this quickly, which is the name of the game for tests. In tests, I won't specifically tell you how to do it first. You could sum the forces vertically, you could sum the torques, and then sum the forces. You could do 2 sum torques and get the same thing. I'll leave it to you. But typically, the procedure that I usually do is you choose one point that makes the other force irrelevant, you sum the forces, sum the torques is equal to 0 and find one unknown, and then you do sum the vertical forces is equal to 0 and find the other unknown. I'll be with you in a second. Yes, Adrian.
The R2 plus R3 times torque, or times T.
Mm-hmm.
What does that stand for? The distance from the force to the...
What is torque? It is the distance from the rotation point to the force. So that is the rotation point. That's the force. So if that is the rotation point and that's the force is tension, the distance is R2 plus R3. All you have to do is pay attention to the distance from the force to the rotation.
Point is the fulcrum.
Mm-hmm. Yeah, it was stated, I stated earlier that rotation point is the fulcrum. So that's it. All right. Any other questions on this? Going once. Going. Heard somebody. All right. Going once. Going twice. Sold. Class closed.